Okay, so next group, um, okay, resonant or tuned circuits, and I think this is the last group on this one. Impedance, which is represented by a Z, is in opposition to alternating current flow. Now, if you want to get an idea of what it does, remember that resistance is opposition to all types of current flow. But when we talk about impedance, it is resistance, but it only resists alternating current flow. And it is still measured in ohms. So Z is equal to R plus J times the difference between XL and X sub C, X of L and X sub C. And there's some other formulas there. X of L is equal to 2 pi FL, and X sub C is equal to 1 over 2 pi FC. So remember that L is just a straight formula, and when you're calculating X sub C, it is going to be 1 over. Your capacitance is going to be 1 over. So inductive reactance, which increases with frequency, and capacitive reactance decreases with frequency. This will be used later on when you start trying to plan out your antenna, because certain things can happen if you add a capacitor or add an inductor. Resonant or tuned circuits. Resonant or tuned circuit inductors and capacitors. This symbol or this drawing that you see here has got an inductor on one side and a capacitor on the other side. And as it goes back and forth, theoretically, it should stay pretty even, but you're going to have some losses in there at some point. Series, very low impedance at the resonant frequency, and parallel will have a high impedance at the resonant frequency. An LC circuit is resonant when the inductive and capacitive reactances are equal. And okay, so if X sub C and X sub L are equal, the only resistance you would have left in the circuit would be whatever DC resistance you have, which still affects AC. But as far as the AC goes, that's as close as you're going to get to the regular DC resistance of the circuit. The energy is transferred between the magnetic field and the electrostatic fields. The drawing here you see shows your impedance on the vertical and your frequency on the horizontal. And then you'll notice the red line there shows your DC resistance. And then the capacitor line will show how it reacts to changes in capacitance or changes in frequency. Let's see. Minimum impedance at resonant frequency. Let's see. Series. So you see in the first one there, you have a series circuit. There's no other places for current to go. So it's going to have a minimum impedance at the resonant frequency. This is going to be as low as you can get it. Only the circuit normal DC resistance is the only resistance that will be there. Maximum impedance at resonant frequency on the one on the right, because you have a parallel paths there for current to flow. It's going to, you're going to have maximum impedance at the resonant frequency. Let's see. What am I looking at here, Bob? Series is on the left. Okay. Okay. Yeah. Okay. Oh, so the one on the right is supposed to be parallel resonance. Okay. Yeah, it's just labeled wrong. Okay, so, yeah, so what Bob was saying is, what's that? Uh, circuit current. Okay, yeah, because, okay, so I see what it is. So they are both resonant, or both series, but the one on the left is showing resistance and the one on the right is showing current. Yeah. So as the resistance, as your impedance decreases toward whatever the value of the DC resistance is, your current at the same time is going maximum. Okay, and on parallel, it is just the opposite. Your parallel resonance is going to increase, or I'm sorry, your parallel resonance is going to increase towards its maximum as you get closer to the resonant frequency, and at the same time, you'll notice on the right, your current is going to decrease. Because we all know current decreases when resistance increases. Which of the following is a resonant or tuned circuit? Okay. Alpha, Bravo, Charlie, or Delta? Who's got an answer? Alpha. It sounds like everybody agrees with alpha. An inductor and a capacitor in series or parallel. And what it says out here on the right-hand side about reactances cancel. Remember, at resonance, X sub C and X sub L are equal. Which of the following is combined with an inductor to make a resonant circuit? Capacitor, required to cancel the inductive resonance. Other components, switches, open and closed circuits, switches and input or output between two or more circuits, single pole dual throw or single pole SPDT switch, connects a single circuit between two other circuits. So you've got a battery over here on your left, and you're going to connect it to either the light bulb or to the LED, one or the other. So that's all they're showing you there is that S1 is set up to choose which circuit you're going to power up. And this is the same drawing we looked at a little earlier. Everybody remembers that. What is the function of a single pole double throw switch? C, single circuit is switched between one of the two other circuits. Relays, electrically controlled switch, and anybody that's ever worked on your cars probably had to deal with these at one point or another. Voltage on the input of a relay causes its output to switch. So you've got your 12 volts out here on the left, and your switch to turn it on. When you turn it on, there's current flow through the coils, which draws the switch over to it, the switch that you're trying to control. So you've got normally closed and normally open, and then you've got your LED up there at the top. When there's current through this circuit and it draws the switch over, then you have it's open. Your switch is open, so you should have no light on your LED there on D1. Open this one up over here, open switch 1 over here, current through the inductor shuts off, the spring in the relay brings it back to normally closed, and you should have your 5 volts down there will be connected to your LED, and you should have light. And that's used for lots of different things. What is a relay? An electrically controlled switch, A. Other components, meters display an electrical quantity as a numeric value. So like the circuit we just looked at, you knew that it was on just because your yellow light came on, your LED came on. But in this case, we don't just want to know that it's on, we want to know what the voltage actually is. So you use a meter. Displays an electrical quantity as a numerical value, analog or digital. So the one that I use at work is a digital multimeter, and it gives me a representation there of what I'm testing. The one that I have at the house is an analog meter. It's got a scale and a pointer, and it points to 13.8 all the time. Output voltage of a power supply, output power of a transmitter, and many other different values. I mean, the one that I've got at work, almost 20 years ago, I paid $500 for it. Now it's no longer produced, and it's starting to fail, and I need to replace it, and I'm just hoping that it can last another 16 months till I retire, because I don't want to spend $900 on another meter this close to retirement. Anyway, I can measure all kinds of values, and here's a representation of some of the common meters that you might see while you're looking around at various electronics things. Now, to see these meters, you're probably going to have to look at vintage electronics. They've been around a while. And then there's some digital panel meters. I've got some of these that are about the size of a 50-cent piece that can be used almost anywhere. You just cut a little hole that they fit in, and it clips in there, and then you can attach leads to it and know how much your battery is inside the box. Or you can set it up to different ones. You can set them up to tell you the current draw and things like that. Which of the following displays an electrical quantity as a numerical value? A meter, C. Other components, let's see, integrated circuits, combine semiconductors and components. This is really the big breakthrough that has gotten us from like the 60s and 70s into what we have now, because without ICs, this wouldn't be possible. Nor would this. But anyway, single substrate, usually silicon, contains many electronic components. They're built on top of there, and they're really, really, really tiny. But they all do, like I say, they all do a job for something there. Microprocessors, millions of transistors inside them, analog or digital functions. Voltage regulator, power supply, and voltage control. So your voltage regulator is pretty much any place that you're generating a supply of your own. You have to have a regulator, because there are a lot of things that can cause it to rise or fall. So you want to have a regulator in there so that it stays fairly constant. Digital counters for frequency counting, test instruments. So all this stuff is being done through integrated circuits. And there's an example of an integrated circuit right there, if you can see it from where you're at. If you get to look at one like this in the shop, you've probably done something wrong. What's that? Yeah, blew the top right off of it. Reference voltage circuit. So in the circuit that you see there on the left-hand side, it shows you've got a reference and your voltage. Let's see, and you inside the blue circle there, what do you call that? It does kind of look like a capacitor. Somebody got lazy and didn't draw enough lines to make it look like a voltage regulator. But yeah, that's so. But what's that? Yeah. So anyway, circuit that outputs a voltage used as a criterion for determining whether or not an output voltage is higher or lower than the required voltage. So they're using it to keep the output voltage steady. Is essentially what they're doing there. And that's, like I say, that's important. What is the name of a device that combines several semiconductors and other components into a single package? An integrated circuit. C. Let's see. What type of circuit controls the amount of voltage from a power supply? A regulator maintains constant voltage output from a higher voltage power supply. Fuses break the connection. These are fairly important. And remember, I told you earlier in most of the drawings that I have at work, the fuse is represented by a sine wave with wire at each end. So that's what you're seeing right there. F1 is a 500 milliamp fuse. And you've got a pulsing output there or pulsing input there on V1. Current goes up in this instance. As current goes up, the voltage drop across R1, which is a fixed resistor, is going to increase. But the current through F1 is the part that's going to cause that fuse to burn out. The wires inside these fuses are, I've actually got a brother-in-law that works at a plant that manufactures the wires that go inside of fuses. They don't manufacture the whole fuse. They just manufacture the wires. And it is, they're all designed to burn out at a certain rate, plus or minus. There's always a variable there. And there's many different types of fuses there. If you look at the one there, the cartridge fuse. The cartridge fuses right there can be very easily mistaken. They won't light up, but they can be very easily mistaken as an LED. And I have a Dell Inspiron 1, one of the all-in-one computers at home, one of the first ones that ever came out. And I've repaired that power supply in there 3 or 4 times. I'm not repairing it anymore. It's done now. I'm just waiting to take the hard drives out of it, and then the rest of it's going to recycling. But yeah, Dell, I think what they did when they designed that computer was to say, look, we've got this odd-shaped power supply. Let's see what we can bolt to the outside of it to make a computer. And in order to repair that power supply, I didn't buy a new power supply because a new power supply at the first time it blew up was like $320. Ridiculous price for a power supply. But I opened it up, I did some troubleshooting and replaced a few components and fixed it. And it's blown up, well, now 3 more times since I've had it. But that was kind of odd. That was the first time I'd ever seen a fuse that looked like an LED. And I've still got, I ordered 5 of them, and I've still got 2 of them at home somewhere. But, yeah, it's like a 95% disassembly to get to the power supply to repair it. I'm just tired of taking it apart and putting it together. So anyway, all those there are various different types of fuses. The wired fuses there, you'll see the ones on the right side of that line there. Those are called pico fuses. We have those in a lot of the equipment we work on at work. You know, the blade fuses are what's in everybody's cars these days. And I don't think I've ever seen the poly fuses, and if I did, I probably thought they were capacitors because I don't remember ever replacing any that looked like that. And then you probably have a couple of those high current fuses in your car somewhere. But anyway, those are all different types of fuses. What electrical component is used to protect other circuit components from current overloads? A fuse. Opens a circuit to protect what hasn't already been damaged, because they're usually a little on the slow side. Not as slow as a circuit breaker. Speaking of slow, I have solar panels on my roof. I've had them up there for about 3 years, 2.5, 3 years, something like that. And I've had to replace the fuses in that twice because of lightning strike. And I was looking at it, and they decided to go with slow blow fuses in there. And the difference in cost between a slow blow fuse and a fast acting fuse, the slow blow fuse is about 3 to 4 times the cost. So I spend $20 to replace those fuses where I could have spent $5 on the fast acting, but I can't find any information that tells me if you can use a fast acting fuse in there or not, or if it would be going off all the time. Shielded cables prevent coupling of unwanted signals, and this is something that may affect your station at some point or another. On just a regular wire with no protection around it, no shielding around it, you can sometimes get unwanted signals in there. So when we're doing things, we have twisted pairs, we have shielded pairs. There's all kinds of different wires you can use, but if it says that you need to use a shielded wire, shielded coax or something like that, be sure you use the shielded. May have multiple conductors inside, as you can see there. It's got 4 different conductors inside it. The shield will typically be connected to a ground. Now, in amateur radio, most of the time that foil there that you see wrapped around the inside, most of the time that's going to be a braid. And that will be connected to the ground some way or another. The shield acts as a Faraday cage. And Faraday cage keeps unwanted electronic signals outside, or in some cases can be used to keep them inside. And this gives you a couple of examples of a Faraday cage. Faraday cage in the absence of an electrical field. So all it is a metal wall. The second drawing there, you see charged particles in the wall of the Faraday cage respond to an applied electrical field. And in the third one, electrical fields generated inside the wall cancel out the applied field, neutralizing the interior of the cage. So when you put, you see the third one here, you have a positive and a negative there at the top. So when you put a potential on that, it keeps everything from the inside. That's why your shield has to be connected. It has something on it to keep anything outside from getting in. Which of the following is a reason to use shielded wire? C, to prevent coupling of unwanted signals to or from the wire. And coupling is real. I demonstrated this to myself when I was trying to tune my 10-meter dipole, the first 10-meter dipole that I built. When I was trying to tune it, I just suspended it right alongside on the same rope that I have my 40-meter end-fed on. And then wondered why, while I'm sitting there looking at it and nothing's moving, why my line was all over the place. And it was because it was coupling to that 40-meter antenna. Once I took the 40-meter antenna down and got it out of the way, it's just as flat as could be. Okay, takeaways. Resonant circuits. Series resonant, very low impedance at resonance. Parallel resonance, you have very high impedance at resonance. Switches, single pole, double throw, single circuit switched between 2 other circuits. Relay is an electrically controlled mechanical switch. So it is a mechanical switch. There's something in there moving, but it's controlled electrically with a coil and a something magnetic. So when the coil energizes, it pulls it out of the way. Meters display numeric value of a quantity, integrated circuit, multiple analog or digital devices in a single package. A regulator maintains constant voltage from a higher voltage source. A fuse protects other components from excessive current. And fuses are faster than circuit breakers. So you wouldn't want to replace a fuse with a circuit breaker just because it's blowing the fuse all the time, because circuit breakers react a little slower. So if it's supposed to be a fuse, be sure it is a fuse, not something else. Shielded, and keep it the same value. Shielded cable prevents coupling of unwanted signals.